Within the Introduction to Statistics playlist, we already discussed the introduction to the binomial distribution. So if you needed to learn some of the more basic and introductory concepts as it relates to the binomial distribution, I would recommend you take a look at that video now. However, if you're only interested in computing binomial probabilities in R, please stay tuned and we will walk through the various steps to achieve that. But if you're interested in what's actually going on within the R system, you might want to check out the Introduction to Binomial Distribution video. As always, code is in the description, and the code that you're going to need to run prior to beginning these exercises is this code right here. And what this will do is it will disable scientific notation within your R session for the remainder of the session. And again, we're going to be using RCommander to run through these examples. So if you need to learn how to install RCommander, there's also a video on that in the playlist. So in this case, for this particular example, we're going to roll 13 dice. It's a fair die for each one of the dice, and each die, therefore, would have 6 faces, and each of those faces contains the number 1, 2, 3, 4, 5, or 6, because it's a perfect cube. We want to know the probability of exactly 5 dice showing the face of 6 on 13 rolls. So again, looking at the symbolic notation as it relates to the binomial distribution, P is the probability of success, Q is the probability of failure, N is the number of rolls, X is the number of successes necessary, and P, X equals 5, is what is the probability that 5 rolls will show the face of 6. So how would we achieve this calculation in RCommander? We've already done it in R as it relates to the Introduction to Binomial Distribution video within the Introduction to Statistics playlist, but how would this calculation be completed within RCommander? So I'm going to do this one in RCommander itself, and then we'll look at the slides, and then for the rest of the examples, we'll just consider the slides because it's easier to see the output. So here is RCommander, and here is our R session. So let's get RCommander up. So as you can see, I've already disabled scientific notation. Take this code that's in the description and just submit it. And I've already submitted it, so it's giving me a bit of an error there, but go ahead and submit it yourself to disable scientific notation. Next, we're going to go to distributions. We're going to go to the discrete distributions, because binomial is a discrete distribution. We're then going to go to binomial distribution and binomial probabilities. The number of trials is 13. N equals 13. That's how many dice we're rolling. And the probability of success is 1 out of 6. So 1 divided by 6 is 0.1666, and 6 repeating. So I'm just going to go ahead and put 3 6s in there. Actually, we'll keep it 3 significant. Now we'll do, here we go, 3 6s. And then we're going to go OK. So this is the code that RCommander has assembled and is running for us. And the output related to that code is right here in the R console. So we'll talk about how to break down this output to discern what the answer is to your inquiry. But let me go back now to the lecture slides. So this is, again, demonstrating the steps that we've already embarked upon. And as you can see, N equals 13, so 13 goes there. Probability of success, 1 divided by 6 is 0.166. So it looks like in this case, on the slides, I've only used 3 significant figures. So probability of success is 1 out of 6. Probability of failure is 5 out of 6. Number of rolls is 13. And number of successes necessary is 5. So what is the probability that 5 rolls will show the face of 6? So this is the output within the R console. We have to count to 5, 0, 1, 2, 3, 4, 5. And this right here, this is the probability figure. So the probability of it rolling exactly 5 sixes on a fair die is 0.037, and then you have to multiply that, move the decimal point over 2 places, and we get 3.7. Now, depending on how you're handling significant figures, you might want to round it, etc. But in any event, this is the console output. Multiply that, move the decimal point over 2 places, and then depending on how many significant figures you're utilizing, do the appropriate rounding. So now let's compute the probability that at least one die showing the face of 6 will show up on 3 rolls. So at least one die. Not exactly one die as we did, or excuse me, not exactly 5 dies of our dice as it was in this problem. In this case, we want to know the probability of at least one. At least one. All right, so get in the habit of defining exactly what it is you're looking for. Whether you're looking for an exact number of a certain outcome, exact number of successes, whether you're looking for a number greater than that particular number of successes, a number less than that equal to that number of successes. Make sure that when you're running these tests, applying these methodologies, that you understand exactly what you're looking for and you structure the code and the test and the methodology appropriately. So in this case, we want at least one die showing the face of 16 on 13 rolls. So the probability of success is 1 out of 6 because we only are interested if it's one die or more. The probability, or we're only interested in a face of 6. A face of 1, 2, 3, 4, and 5 we're not interested in. So there's only on a single roll the probability of 1 out of 6. 1 out of 6, because there's only one face of 6 on a die that has 6 faces. We're rolling 13 times, and we're only interested in at least one die roll. So it could be 1 6, 2 6s, 3 6s, 4 6s, 5 6s, all the way up to 13 6s. So at least 1 6. So P X greater than or equal to 1 was the probability that at least one die will show a face of 6 on 13 rolls. Well, in the case of this prior example, was the probability that 5 rolls exactly will show the face of 6. Okay? Know the difference, know when to apply the difference, know exactly what it is you're looking for. Maybe write it down or underline if you're given a word problem. So in RCommander, you'll go to Distributions, Discrete Distributions, Binomial Distribution, Binomial Probabilities. N is going to equal 13. Probability of success, it looks like we're keeping it at 3 significant figures. 1 divided by 6 is 0.166. So the probability of success is 1 out of 6. The probability of failure is 5 out of 6. We're rolling 13 rolls, and the number of successes necessary is 1. So what is the probability that at least one die will show a face of 6? At least one. So this is a little tricky. For this, we have to get the 0 value. And from that value, we subtract that value from the number 1. So 1 minus the 0th value in the list of elements here. 1 minus this value here 0.094440587, so on and so forth, equals this value here. And then again, determine how you'd like to round, significant figures, etc. But in either event, you have to turn it into a percentage first. The probability that at least one die will show a face of 6 on 13 rolls is 0.905, or 91%. Looks like we're putting the decimal here, and then we're rounding it up. 91%. Compute the probability of rolling more than 4 sixes, but less than 8 sixes on 13 rolls. More than 4 sixes, but less than 8 sixes on 13 rolls. Okay, it's going to get a little tricky here, all right? So here is how this probability would be notated. P, X is greater than 4, and P less than 8. So what's the probability of rolling more than 4 sixes, but less than 8 sixes? So more than 4. So that would be, but less than 8. So distribution, discrete distribution, binomial distribution, binomial probabilities. 13 rolls, 1 out of 6 is our probability of success, because we're only looking for a single face. So what is the probability of rolling more than 4 sixes, but less than 8 sixes? Well, 5 is greater than 4, 6 is greater than 4, and 7 is greater than 4. 8, as far as 8 is concerned, 7 is less than 8, 6 is less than 8, and 5 is less than 8. So we're only interested in more than 4 is 5, 6, and 7, and less than 8 is 7, 6, and 5. So it has to adhere to both limitations. More than 4, but less than 8. So that leaves 5, 6, and 7. So what is the probability of rolling 5 sixes, 6 sixes, or 7 sixes on 13 rolls? So we're rolling 13 dice, and we're looking for either 5 of those dice being all sixes, 6 of those dice being all sixes, or 7 of those dice being all sixes. So the probability of rolling more than 4 sixes but less than 8 sixes on 13 rolls is 0.050. So again, you have to turn that into a percentage. How you handle significant fingers is up to you as far as rounding is concerned. But again, remember to move this decimal point over to get to the percentage. And we're going to add the value of 5, 6, and 7 from this list. And that gives us the value here. So that is it for probabilities, binomial probabilities that is in RCommander. I hope you found this video helpful. Be sure to check out Introduction to the Binomial Distribution if you haven't done so already. It might be helpful in clearing up why we're doing some of this as it is. And if you made it this far, I appreciate it. Please consider liking and subscribing, and have a wonderful rest of the day. Take care.